Toolbox, and some demonstrations are there for today, which includes the MPPT boost charger, and then co-simulation with the DSS and the Typhoon Hill, and demonstration of the IEEE 34 node bus system. Okay.
Correct.
Yeah. So, good morning, dear participants. This is Prajay Raikar, research intern from Quabs Info Systems, and today we are going to start off by modeling a four-node IEEE test feeder. Okay. So, before we could start, I will show you in the example section where that model is available for your reference. Okay. So, to find that model, you have to go to this example section, and under examples you're going to find the last category, that is your power systems. Here you have to expand this category. Okay, and this is the IEEE 4 node test feeder that we are going to simulate today. Okay, this is the test feeder, and before that, before we could start, we have to formulate the measurement nodes, that is this node 1, node 2, node 3, and node 4. Okay, so before we could start with the modeling of the entire circuit, we are going to start by modeling this node part first. So what is there under the node is the measurement section. There is a three-phase meter inside this node, and it is a subsystem that has been created just for the measurement purpose. Okay, and it is deployed at this four nodes across the distribution network. Okay, so before yeah, so uh, I have already briefed you what all we are going to go do today. So we are going to start with the modeling part first, and after the modeling part, we are going to head on to the demonstration part and the introduction to the toolboxes. Okay, so with that, I'm closing this section. I'm opening a new model in the schematic editor. So clicking on the schematic editor, okay. So I will open a new model. So I'll select this, create a new model from the toolbar. Okay. After that, I will go with the hardware product as Hill 402 in configuration ID 1, and the simulation setting, that is for a plant part. For my plant part, the simulation method I'm going, that is default exact method, and the simulation time step will be auto. Okay. So remember this simulation setting is for the plant part, okay, and not for the controller part. So I'm going to click on next. So I reviewed my settings. This is fine, and I click on finish. Okay, so now that the new page has opened for the schematic, so first I'm going to formulate the four measurement nodes that we are going to deploy in the network, and then we'll start with the main network. Okay, so for that I'll require a three-phase meter. Okay, for that I'll go to this microgrid section. There's a section called meter. Okay, I'll drag and drop a three-phase meter. Okay, then I will require a meter split. This is a special component that is supposed to be used with this three-phase meter. Okay, because this three-phase meter is capable of doing many measurements, and those measurements can be systematically collected by using this meter split. So with that, I will start with the meter first. Okay, for this meter I have to do some settings. uh, I will double click on this meter to open its properties. Okay, I will provide the snubber resistance here in the general tab as R snubber, and this value of, I mean, the value of this variable will be initialized in the model initialization script. Okay, and the number of RMS cycles for estimating the RMS value will be R RMS underscore cycles. Okay, and the execution rate will be TS. I will disable the internal probes. Then I'll go to this section called as voltage, and under voltage I'll enable phase as well as the line voltage measurements. Okay, for currents I'm going to enable all three currents. For frequency I'm going to enable the frequency measurement. For voltage RMS I'm going to enable this two measurements for phase and the line voltages. Next is the current RMS. For current RMS I require the phase currents, and for power I want the measurement type to be RMS based, and the power measurement will be enabled. Okay, and with that I'll say okay. So my meter is set. I will recheck. Okay, and I'll close it. Okay, and next I have to connect this output with the meter split. Okay, so all these measurements which are there in the meter, three-phase meter, will be collected by this meter split, and then we'll use it to display it on Scada. Okay, for meter split we have similar arrangement to decide which signals we want to view. So I'm going to disable all this. I will go to line voltage and I'll enable all this measurement. Okay, except the last one, the average value I'm not interested in. Going to the current section. For current, I'm going to repeat the same one, that is enable everything except the average current measurement. Next, I'll go to the frequency measurement. No need to enable the frequency. Moving on to the power measurement, I'm going to enable all four power measurements. Extra measurement, I'm not going to take anything, so I'm going to say okay. So as you can see, since there are many signals on this output port of the three-phase meter, now we have got, because of the meter split, we have got proper arrangement or the proper visual which signal is going where, such that we can easily collect the required signal. So we can resize this. Okay. Okay, after that, we have to connect some tags at the output such that we have to route this signal to a different section of this controller. Okay, I'll zoom over here. And I'll go to this systems. Okay, from the systems, I'm going to take signal go to tag. Okay, I require around 6 go to tags. Okay, and I can hide their name. And now I'll start connecting. Okay, next is to rename these tags. So the first voltage VAB tag I will be renaming it as V1. So I double click and I'll rename it as V1, and I'm going to keep the scope as local. The second tag will be V2. Third tag will be V3. Fourth tag will be I1. Fifth tag 2, and the last tag will be I3. Okay, so my tags are set. Next, to add proofs to this RMS measurement and the other power measurement such that I can transfer them to the Scada panel. Okay, so I'm going to go to this signal processing section, expand it, go to sinks and drag and drop probes. Okay, so I've dragged and dropped probes. So I will rename the first probe as V1 underscore RMS and say okay. This second probe, I'm going to rename it as V2 underscore RMS. Next probe, so this spacing is fine for me. Okay, third probe will be V3 underscore RMS. I'll add next probe, which is I1 underscore RMS. Next probe will be I2 underscore RMS. So I see I'll add I3 underscore RMS. Okay, now it's time to add the probes to this PQ, S, and PF measurements: active, reactive, apparent, and the power factor. So I'll rename this probe as P. Next probe as Q. S, and the last probe will be PF. Okay, so we have added all the required probes and the tags. Yes, so next is to formulate another part here. Okay, now I require the tags that are called as signal, from, okay, I have taken 6 of those tags and I require the 6 probes. Okay, we can hide their name. Okay, tag number 1, rename it as V1. Tag number 2 as V2. Tag number 3 as V3. Tag number 4 is I1. Tag number 5 is I2. And tag number 3 is I3. Okay, accordingly, we are going to name that probe same, V1, V2, V3, I1, I2, and I3. Okay, next we connect these tags with the probes. Okay, so we have completed this part. Next, we require this tags again. So I'm copying it and pasting them again here. And next we are going to take a bus join. So within signal processing, we go to the systems and we drag and drop a bus join. Okay, we double click and the number of inputs you need to set is 6. Okay, so here we have expanded the number of inputs. Okay, next we connect V2 and then V1. Next we connect I2 and then I3. And at the output we require to measure the phase difference. So we require a phase difference block. So under power measurements within signal processing, we have this option for measuring phase. Okay, you can see this is called as phase difference block. And once after placing the phase difference, we require to split the signals again. So I'll take a bus split, double click on it, expand its output to 6 in numbers, and then connect this phase difference. Okay, next we need to add the probes here at the output. So I'll go to sync section of the signal processing and drag and drop probes. Okay, I have 6 probes. Okay, I'll rename first probe as V1 underscore phase. I'll rename second probe as V2 underscore phase. Third probe as V3 underscore phase. Fourth probe as I1 underscore phase. Fifth probe is I2 underscore phase, and the sixth probe is I3 underscore phase. Okay, now we connect those probes at the output. Okay, I'm just checking if the tags are matching over here. So under matchings, you should get this tag number. That means the tag is matched. And if you click on it, it will take you to this tag that was there linked with that. Okay, so that we have completed this part. The next part is to convert this entire controller part or the measurement node into a subsystem. So what we'll have to do, we'll have to select this entire portion and we have to right click and do create a subsystem from selection. Okay, once we do that, you can see we are no more in the root schematic, we are in the subsystem. So automatically the open ports have got the ports now here. Earlier they were open, now they have got proper ports. Okay, also you can see there's a port that was added to this reference. We had kept it open. Okay, so we have to assign an index for those ports such that they appear on the right or the left side or the top or the bottom side of the subsystem. So starting with this port, I'm going to double click on it. I'm going to keep its side as left index 1 and hide its name. This will be left 2 and hide its name. Whether this port will be left at number 3, hide its name. Okay, similarly these ports will be right 1, hide its name, right index 2. Okay, this will be right index 3 with hidden name and say okay. Next is this P1, this should be ground. So this will appear at the bottom one and I don't want any label for that port and I'll say okay. Okay, so the index has been assigned. Next is this port. This port has to appear at top. So I'm going to right click, set the side as top and index as 1 and going to hide its name and say okay. Okay, so that completes our subsystem part. So let's go to root schematic. As you can see, this is the subsystem that we have formulated now. Okay. Okay. This subsystem we are going to rename by double clicking on its name as node 1 and going to say okay. Okay. Next part is to mask this subsystem. So we are double clicking, not double clicking, we are right clicking on it. We go to mask and mask editor. Okay, if you do look under the mask, you are going to see what we have what we have inside the subsystem. So we are going to add a image on this node. Okay, in order to add the image, we right click and then we go to mask and the mask editor. And from the mask editor, we go to this appearance. Okay. And before we could do this, we will have to save this model. Okay, I'll save it in the existing folder, which is IEEE 4 node test feeder. I'm going to select this folder and I'm going to say IEEE 4 node, and I'm going to save it here. So next, if I show you that folder, the IEEE 4 node folder, I already have the image over here that is called as gauge.svg. So that image I have already pasted in this folder. Okay, so that image I'll be importing on that subsystem. Okay, so I'll right click, I'll go to mask and the mask editor. Next is the appearance. Here you can write the description of your item. Okay, and here in the icon drawing commands we can add the image. Okay, we have to add the image command here. So I will say image, and the name of the image is gauge dot, the extension is svg. Okay, and if I say okay, you can see the same image is pasted here. It is the gauge image. Okay, so next is we can write some description also for that subsystem. If we double click now, we won't be able to penetrate this subsystem. So in order to penetrate, you'll have to go to mask and the look under the mask to view this section of the circuit. So here we do mask and the mask editor, and if you go to appearance, then here we can write the component description like node subsystem consists of following measurements, that is current RMS, current phase, voltage RMS, voltage phase, it is powers, active, reactive, apparent, and finally it has a power factor measurement. Right, power factor. So we have written the description, and with that we are going to say okay. So you can see the same description has appeared here. If you double click, you'll get the information about the subsystem. So this is a small demonstration how a subsystem can be made. And next we are heading on to the main circuit now. Okay, so now that we have made our node, we'll start off by taking a three-phase voltage source. Okay, so we go to sources and we drag and drop a three-phase voltage source. We require a ground for this. So there is a ground available here. I'll drag and drop a ground also. Okay, this node will come here. We require a voltage measurement for phase voltage. So I'll go to measurements and I'll drag and drop this voltage measurement. I will rotate it right. Okay, and place it there. Next, we require the transmission line model. Okay, so in order to get the transmission line model, you have to go to this section called as transmission lines. Okay, drag and drop a transmission line from here. So from here, we are going to go to this section called as pi section, and from here, we are going to drag and drop a transmission line. Okay, this is the transmission line model. Okay, so I have resized this node as per my requirement. Now I'm going to copy this node and paste the same node ahead. Okay, we need to add the ground also. So I'm going to copy the ground from here. Okay, and add it here. Okay, next we need to add a transformer. So to add a transformer, we are going to go to this section called as transformer. There's a dedicated section for transformers also. So double click to open, and we require a three-phase, two-winding transformer. Okay, I'm going to paste this node ahead of the transformer. And next I require the same model of the transmission line. So I'm going to paste it here. And I'll also paste this node here. And finally we require a load. So load will be constant impedance type load. So for that we go to this microgrid. Then we go to the loads and we drag and drop a constant impedance load. Okay, so the components that we required are here. We need some ground points. Okay, so next we start off with the connection. Okay, we'll connect the ground. We'll connect the voltage measurement. Next we'll connect this node. Okay, next we connect the node with the transmission line and the ground. Okay, next we ground this node and connect the output with the primary of the transformer. Next we connect the secondary of the transformer with node 3 and we ground that node. Next we connect that node with the transmission line 2 and then we connect the transmission line with the node 4 and we ground that node. Okay, next we connect the load to the node 4. Okay, with that we have completed the connection. Next is to rename the required parts. So we'll start by renaming this voltage measurement. So I'm double clicking on it and I'm renaming it V reference. The three-phase voltage source will be renamed as V grid. The transmission line 1 will be renamed as overhead line OHL and dash 2. Transformer, I am renaming it as TRF 2-3. Transmission line 2, I am renaming it as OHL 3-4. Okay, this load we can keep it as constant impedance load. Okay, next part is to give the specifications to the components. Okay, going to starting off with this voltage measurement, the phase voltage measurement. I'm going to double click on it, go to signal processing tab and enable the signal output and its execution rate will be PS, okay, such that we'll get a output port for signal processing. And then we go to this voltage measurement, the voltage source. We double click on it. We specify the RMS voltage as 7200 volts and the frequency will be 60 hertz. We're coming to this overhead line 1-2. We double click on it and we have to just specify the length here. The length is 0.37878737878789. Okay, and then we are going to say okay. Okay, moving on to the transformer. Double click on the transformer. Okay, the input parameters will be in terms of SC and the OC test, short circuit and the open circuit test, and the nominal kVA rating is 6 MVA. Okay, the frequency will be 60 hertz. The primary voltage is 12.47 P3. The secondary voltage is 4.16 P3. The USC one is 6%. Okay, it's 6%. And the PSC one is 60 E3. The core model will be LMRM neglected. Okay, moving on to the winding connection. It will be a delta-delta connected transformer with a clock number 0. And we say OK. Okay, next we move on to the overhead line 3-4. Double click on it. You have to specify the LAN as 0.4734.848 miles. And then we say OK. Okay, coming to the constant impedance load. Okay, the load connection type will be delta. Okay, we are not setting a balanced three-phase power, so this section will be disabled. So we go to the phase A. We specify the voltage as 3446.8 and the nominal line power as 1800 E3 by 0.9 with a lagging power factor of 0.9. And moving on to the phase B, nominal line voltage will be 3501.8 and the nominal line power as 1800 V3 by 0.9, power factor lagging at 0.9. Moving on to phase C, the line voltage is 3388.5 with nominal line power of 1800 E3 divided by 0.9, power factor mode lagging at 0.9, and with that we say OK and our load is set. Okay, next we need to add a tag. So we go to systems, we take the signal go to. Okay, we are going to flip this tag like this. We have to flip this meter also. Okay, no need to flip the meter. You can transfer it like this. Even no need to flip the tag. We can write the name and we can connect the tag and give the name to the tag as V reference. and say OK. Now we have to add this same v reference tag on these nodes. Okay, so we are going to take from tag and we are going to add it. The name will be same. Okay, so we are going to copy the same tags here. Here and finally at node 4. Okay, we have added the tags. Okay, this has completed our plant part. Next is to initialize the variables in the model initialization script. So for that we are going to open this option from toolbar for model initialization script. Okay, this is the scripting window. We have to initialize some of the variables that we have assigned, like the execution rate for the controller part. PS is 100 E minus 6. The RMS cycles is equal to 10. Hours number is equal to 1E5, and we are going to save OK, and we are going to save this model. Okay, and next part is to load this model into the Scada panel. So we are going to click on this compile and reload the option into Hill Scada. Okay, so since we are running it on the PC, so we'll see load model to the virtual hill device. Okay, so we'll be creating a new panel. So we'll say create a new panel and we'll expand the library a bit. Okay, next we have to create a SCADA, the SCADA panel for that model. So we're going to start off by taking the gauge. Okay, I'll drag and drop a gauge. Double click on it. Rename the gauge as active power. And we're going to add the signal. Okay, it's not from here. We are going to change the data type to the expression. Okay, after changing the data type to the expression, the display unit, you can see here display unit. The display unit will be KW. Okay, so now that we have set the display unit, next part is to write a code. So we open this microcode into the code editor. So we click on the edit in code editor. Okay. Next, on the left hand side, you can see there are control commands, capture commands, and the other commands. So we have to go to this other commands tab, and from here we have to select node 1 active power. Node 1.p is the active power that will be measured by the node 1. Okay. After that, we are going to edit this value of 0.0, and we are going to insert the code here. Okay. And next, we're going to divide that reading by 1000, okay, to convert it into kW, and then we are going to save it. Okay, once we save, we close the. Okay, we'll set the range for this gauge. We double click on the gauge, go to advanced setting, and we change the range to 8000. Okay, so the range has changed now. Next is to add the digital displays. Okay, so the display one will be V1 RMS. Okay, for this, I go to expressions. Set the display unit as volts. Open it in code editor. Remove this equals 0. Here I'll set node 1 V1 underscore RMS and insert it. Then save the code and close the window. Similarly, I'll go to display 1. I'll set it as V1 phase. Okay, next we change the data type to the expression. The display unit will be volts. Sorry, it will be in degrees. Okay, so I open the window in the code editor. I edit the value of 0.0 and I add here node 1 v1 underscore phase. And I place the cursor and insert the code. Okay, and then I save the code and close the window. Okay, similarly, you can add for V2 RMS. Okay, I will edit the code here itself. This will be V2 phase. Okay, I'll run the simulation for some time. Yes, it's reading the value. And okay, similarly, we can copy for V3. Okay, I'll edit it to V3. It will be V3 RMS. Here it will be V3 phase, and here it will read V3 phase, and I'll say OK. Next is to repeat the same procedure for I1, I2 and I3. So the respective currents and the phases will be shown here. So for that, okay, I'll say I1 RMS will be node 1, I1 RMS okay, here it will be I2 RMS. The display unit is ampere, and then the signal it has to read is I2. Okay, similarly here has to read I3. The display unit will be amps, and here it will read I3 RMS. Okay, and I'll say okay. Okay, next is the phase. Okay, the first one will be I1 phase. The second one will be I2 phase. And third one will be I3 phase. Okay, so next is to group these widgets. So I can drag and drop this a widget called as group. Okay, and we can copy and paste these widgets here in the group. Okay, and all this entire group is for my node 1. So I'll rename the group as node 1, and similarly we have to repeat for node 2, 3 and 4. So I'm going to control copy this entire group here for node 2. Similarly, I'll edit your node 2, Okay, I'm editing everywhere for node 2, just changing the number. So this is completed for the node 2. Okay, it's running fine. We'll repeat the same procedure for node 3. Okay, so for node 3, we are again going to edit the number for node 3. Okay, next we move on to this I. For currents, we also change to node 3. Okay, finally to repeat the same procedure for node 4. Okay, finally moving on to the currents. Okay, so the panel is running fine. Finally, we can finish off this panel by adding an image. So for that, you'll require this image widget. Okay, we drag and drop this image widget. Okay, double click on this image widget, go to select images, and then we go to our folder on the desktop, that is IEEE 4 test video, and we have a single line diagram here. So this is the diagram which I want to insert. Okay, and this completes the Scada panel for this model. Okay, then we save this panel file. Okay, in order to save this panel file, and before stopping the simulation, and we'll save the panel file as IEEE 4 node, the same name as the schematics, and then we'll also save the settings file. Okay, so that completes this model and the simulation. So I request participants, if you have any doubts, please go ahead and ask. Otherwise, we can take a break over here. Hello, sir. Can we take a break if no participant has a query? Hello, am I audible, sir?
Yeah, Prajay, you're audible. Kindly ask Jena sir for the break.
Oh, yes, sir. Hello, sir. Hello. So I think he's busy.
Okay, it's 12:20, so I think we can take a break up to 12:30
Yeah,
anytime.
okay. Okay, so yeah. So dear participants, we are breaking over here till 12:30. Hello, so am I audible? Shall we start?
Yes, sir.
Okay. So I hope my screen is visible.
Yes, sir.
Okay, thank you. So with that, now we will start off by introducing you to the power system toolbox and the microgrid toolbox. Okay. So for that, we'll just open a new schematic model with the default settings, and I'll show you where are those toolboxes located. So first and foremost is the microgrid toolbox, which is directly visible from the library itself. Okay, so the microgrid toolbox has these categories like your distributed energy resources, your model for the grid, your loads, different types of loads. Then there is a metering elements which are there, out of which one we have used. Okay, so there is a protection related section here. Okay, so starting off with the distributed energy resources. So within the distributed energy resources, you can find the model for a back-to-back converter. Okay, the diesel genset. Okay, there are two types of back-to-back converter. One is the average and other one is switching. Okay, okay, so you can see one is average, the other one is switching. So based on what is the requirement of the output waveform, whether you are developing a controller for a microgrid, then you can use this average model. And if you want to use it for a controller, if you're designing a controller for an inverter specifically, then you can go for the switching model. Okay, so like this, we also have this diesel genset. Okay, so if you see this diesel genset, then this diesel genset is classified as a generic component. Okay, okay, I'll remove this, and this is the generic model of the diesel genset. Okay, sorry, I forgot to show you the interiors of the average and the switching converters. Okay, so if you see this average and the switching components, you can see the average component. Okay, it will be uh, modeled by this signal controlled voltage sources. I'll zoom over a bit. Okay, so this is how they are modeled. Means instead of any power electronic device or any power electronic bridge or anything like that, instead of that they have used this uh, signal controlled voltage sources. So because of this, the overall processing requirement of such average based either it may be this converter or any converter which is modeled as an average converter. So the processing requirement of such converters are less. Okay, so that's why depending on whether you are designing a controller for the inverter or designing a controller for microgrid, you are going to adopt either for the switching type model or a average model. Like this average models are more suitable for designing the components on the microgrid side. Okay, if you're designing a controller for a microgrid, okay, wherein the detailed waveforms are not required for the converters. So if we move to the root schematic, here we have a switching model for the converter, the similar converter, but one is modeled as average, wherein they have used the signal controlled voltage sources. Whereas here, if we see, Here we have the actual power electronic converters. Okay, over here, whereas there it is modeled as the signal controlled voltage sources. So whenever you require you are designing the controller specifically for this power electronics, that time the switching models comes handy, wherein you get that all the details which are there in the switching waveforms. Okay, so that's the reason there are two models. So depending on the availability of the resources on the real-time simulator of Typhoon Hill, you are going to either go for the average or the switching model based on your requirement. Okay, so that is done. Next is the diesel genset. Okay, here in the diesel genset there is a generic component. Okay, so here we have a generic component, and along with that there is a component called as generic UI. Okay, so the I'll expand this component first. Okay, you can see these components, which are the generic component, generally come with a complementary part, that is this UI. So this UI has all the measurements that we need to perform on this diesel genset. We cannot look under the mask of this, but it's a diesel genset. Okay, so for this UI, if we expand this user interface, okay, UI is the user interface here. So this is supposed to get interfaced with these components like this. Okay, so you have seen that we have even in the last model which we have done, so we had used many probes over there. So those probes, sometimes it happens that you need to take so many measurements for this kind of vast models of the microgrid that the development time goes to like it increases tremendously, right? So because you have to drag and drop so many probes and then you have to wire them one by one. So here if you see this diesel genset UI, so if you enter its mask, okay, so here you can see there are many probes, okay, already installed. Okay, so it is going to take the input and it is going to accordingly transfer those signals to the Scada panel through these probes. Accordingly, it can also help the user to provide some inputs to this model. Okay, so there are many SCADA inputs over here defining different different control parameters to be specific. And here you can see it can change so many parameters, okay, based on the SCADA input. And these all are available in the ready-made format through this diesel genset UI. Okay, so that's the purpose of providing the UI with the generic components. Okay, so in order to, if you want more information about these components, then definitely you can refer to this help. Okay, so here you will get the additional information about the power stages and the inputs it is going to take, including the UI. Okay, so next is the energy storage. It is also having the same interface. Okay, I will not elaborate on this, but it is similar. Okay, it takes user inputs and gives the outputs. I'm not going through this infrastructure. Okay, these are similar to the measurements that we have done so far. Okay, coming to the power plant. Power plant also has the generic and the UI plant, the UI part, I mean, and the wind power plant also has generic and its respective UI. Okay, and the same applies to the grid also. So the model of the grid is available along with the UI. And coming to the loads, there is a constant impedance load that we have already used. Okay, if you see under its mask, it is connected in the star configuration currently. So we can change the configuration from here either to star or delta. And depending on the control on the load, you can set either the three-phase control or the individual control on its phases. Okay. Next is the variable load. Okay, this is the load which comes with a UI, the user interface. Okay, next is the meter. So this meter we have already used, the meter with the meter split. And finally coming to the protection. Protection has this SCL, the Schwitzer. Sorry, I did something wrong. Okay, so the Switzer Engineering Laboratories 751 relay is available here with its logic. Okay, for more information, definitely you can refer to the help. Okay, all the protection functions are discussed in detail over here. Okay, then coming to this specific protection functions like undervoltage, directional power, low forward power. Okay, all these functions are available. Okay, and the ANSI code for each of this protection is also denoted over there. Okay, this is a feeder protection relay for the microgrid application. Okay, after this, we have to move to the power system toolbox. Okay, so I'll delete this. Okay, the power system toolbox is available under the signal processing, and the subsection is the power system. Okay, this has the models of the diesel generator governor. Then the different exciter models are there. For example, this is IEEE AC1A exciter or IEEE DC 4B exciter. Okay, there's a model of a steam governor valve. There's a model for steam turbine, IEEE G1 steam turbine, and these all components are listed under this power system toolbox. Okay, this note is available in the documents. Okay, for any additional information on those two models, you can either refer the help, or you can even, if you navigate to this page called as power system toolbox, from here you can click on this specific components. Okay, those are the links, so it will link to that specific components along with its model and the description of the inputs and the outputs along with the properties window. Okay, so that concludes the explanation of this power system toolbox, and same thing is available for the microgrid toolbox. Each and every component is described in detail over here. Okay, now we move on to the demonstration of the MPPT boost charger first. Okay, so in order to open the MPPT boost charger, within the examples, we go to this uh, general power electronics. Okay, within general power electronics, we have this option for MPPT boost charger. Okay, So we are opening this model now. Okay, as you can see, this is the model. There is a PV panel at the input. There are measurements for the current and the voltage. uh, there is this inductor, the resistance of the inductor coil, then followed by we have a boost converter, and then at the output of the boost converter we have this filter capacitor along with the equivalent series resistance modeled, and then we have this in our output voltage and the current measurements, and at the output we have this battery and the load. Okay, so the load is sectionalized into two parts over here. One is called as R discharge and other one is R load, out of which one is the higher load and the other one is the lower value of the load. Okay, so the two load resistances are available here, and the battery. Okay, so the battery along with the loads forms the load on this boost converter. Okay, now coming to the MPPT algorithm. So this boost converter is controlled by the piano algorithm, which is taking the input of the PV current and the PV voltage, and accordingly it is computing the MPPT point. Okay, so here the MPPT is coded in this C function block. Okay, this block is called a C function block, and here we have added the delays for the for retaining the past value of the voltage and the currents. And coming to the piano C function block, if we double click on it, this is the C function block, or the properties of the C function block. So here are the inputs that are defined. Okay, so as you can see, for that block there are two inputs. So those two inputs are for the power and voltage respectively, followed by it has outputs. Okay, the output, uh, you can see. Okay, then we have variables. These variables are defined in the program. Okay, so we have defined the variables in advance here, and there are no parameters as such. Okay, next moving on to the functions. For function we have this MPPT algorithm code. Okay, this is the general algorithm that you can even Google and get it. Okay, then comes the initializing function, wherein the duty cycles and the step of the duty cycle is defined. Okay, we don't have any kind of update function for this, and that's a piano algorithm, and accordingly it is going to generate the duty cycle that is given to this tag called as reference. Okay, this tag directly goes here to the boost converter. Okay, the reference that is generated will be coming here to the boost converter, and then it will be generating a duty cycle. Okay, I'm sorry that I said a duty cycle here, but yeah, so that is how it is going to work. The enable tag is will be controlled by this part, and if you see, this part computes the output voltage and the current. Okay, sorry, it takes the output voltage, and accordingly the output voltage is compared with respect to the battery that is connected at the output. Okay, so the battery slow limit is the 49 volts, and the higher voltage is the 52 volts. So the battery voltage is kind of kept in this in between these two limits, the 49 and the 52 volts. Okay, accordingly it the comparator outputs the high or the low value, that is 1 or 0, and depending on that SR flip flop is triggered, and depending on what's the value of the its non-inverting output, the boost converter can be enabled by this enable tag here. Okay, so once it is when the battery voltage is below I mean when it is below 52 or above 49, then it is not going to trigger. Whenever the battery is going to hit this limit, uh, uh, sorry, I said it wrong, but whenever the voltage is going to go below 49, it is going to start charging and going to get it up to 52, and then again after hitting the 52, it is going to again disconnect the charging, right? So that is how it is going to enable and disable this boost converter. Okay, so with that we have covered all the parts of this boost converter. So I'll compile this model and reload this model in the Scada. Okay, we'll select a panel. Okay, and we'll run this panel. Okay, I will initialize the panel. Okay, so here I have loaded the panel called as Jinko JKM 200M-72. Okay, this is in IPv6 file format. Similarly, you can use any kind of uh, PV models file in order to load here. Okay, so here we are tracking the MPP, and the MPPT tracking is visible here in like live tracking on this graph. Okay, and here we can change the irradiance of the PV. Okay, change the temperature, and we can see the corresponding change in the PV and the IV profiles of the panel. Okay, so here the gauges are reading the battery voltage and the battery current. Okay, then there are PV power measurement and the output power measurements on the right, and then there are load currents. Okay, this is the output current of the boost converter, and there is a current through the uh, this is the discharge current on the load side. Okay, so here you can provide the SOC of the battery, the initial SOC. Okay, these are the waveforms in the capture and scope. So here they have the VPV and IPV. So here we have V out, I out, and the battery voltage. Here we have the power from the PV. Here we have the uh, pulses that are going to the boost converter. Okay, and here the load contactors which are there. Okay, these two contactors which are there, those can be controlled. The first contactor is called a load contactor, and the second contactor is called as discharge contactor. So those can be controlled here via this combo box. Okay, here you can see the discharge current. Okay, for different irradiation. So on the PV monitor, you'll be able to observe the current that is being drawn from the panel. The voltage is being outputted, the power of the MPP, and the efficiency with which the MPP is being tracked. Okay, so uh, I request participant, if you have a doubt at this point for this model, then please go ahead and ask. Okay, if there are no doubts, we are moving on to the next model. Okay, the next model will take ease of the OpenDSS toolbox for power systems. So for that, we go to this last section of the power systems. Okay, here we have the same example which we model and simulated today, that is IEEE 4 test feeder, and there is a model of OpenDSS power flow co-simulation. Okay, this is the model on which there is a co-simulation, and the advantages of the platforms are used in order to do a load flow study. Okay, so the OpenDSS stands for Open Distributed System Simulator. Okay, so the same simulator is the the functionality of the same simulator is imported via Python in the Typhoon Hill simulator in the Scada panel. Okay, so here if we open the model, okay, so here is the model. There's a PV panel connected at the input. This is the average model of the PV plant. Okay, if we see the inside, there is no power electronic converters that are present here. Instead, there are again extra signal controlled voltage sources inside. Okay, so and there are controllers. Okay, on the grid side, this is the subsystem. We enter the subsystem, and here there's a three-phase meter which we already used today. There are voltage and the current measurements, and uh, there's a voltage sources that are modeling the grid. Okay, along with there are power measurements. Okay, which are measuring active and the reactive powers for the respective phases. Okay, these are PV in and PV out are the two subsystems. They consist of these inputs in the form of SCADA inputs. There's a bus join here. Okay, and this small system has been translated into a subsystem. Okay, that forms your PV input, and for the PV output, you have just a single probe inside. Okay, and there's a model of the PV panel. And next is this enable, which you can control from Scada. Okay, so this model is the ordinary model in Typhoon Hill, and the co-simulation is done in the Scada panel. Okay, so for that we'll have to load this model into the Scada panel. Okay, so we open our co-simulation panel. So this panel has many sections, as you can see. On right hand side, it is the panel for the Typhoon Hill model that already there in the schematic, and that's what I have described just now. And here in on the left hand side, you can see there's a this tab is of the open DSS. Okay, this handles all the part of the load flow studies. So in Typhoon Hill model, we can read the active and the reactive power. Okay, and all those buses are basically assumed as a PQ buses. So the voltage and the angle delta for those respective buses and the respective phases are computed in by using the OpenDSS platform. Okay, so here if we open this panel initialization dialog, here you can see the file called as open dss direct. Okay, this is the file that has been imported here, and it reads the active and the reactive power on the uh, Typhoon Hill model or the schematic model, and then it actually samples those P and the Q value, the active and the reactive powers, and then it transfers and converts them into the voltage and the phase angles at the respective buses. Okay, for example, you can see here the panel currently is in the is not in the co-simulation mode. Okay, the co-simulation is disabled over here. Okay, okay, to just show you visually, I'll show you the application note that is available with that example. Okay, here is the application note, you can refer from here. So this is the model, okay, which we have already seen, and this is the open DSS model to which that those voltages from the Typhoon Hill models will be referred to. And here you can see the from the Typhoon Hill model they are referring P and Q. Okay, and accordingly it is converted into voltage and the angle theta at the respective bus, and then it is again given back to the schematics. Okay, and that we are displaying on the Scada panel. Okay, so this is just a brief example, the brief introduction to how the co-simulation with OpenDSS works. Okay, and then here you can find this how to generate the power flow report. Okay, before that we'll see how to start the co-simulation. Okay, so in order to start the co-simulation, we have already run the panel. Okay, and here we have to if you see this single line diagram which is here at the bottom left corner. Okay, there's a switch that is open. We have to close that switch. Basically this is an animated model, and if you close that switch you can see the switch is closed now, and we have to turn on we have to enable the inverter basically. So we enable the inverter, so as the result of which you can see the Typhoon Hill side panel has got active. Okay, here it is reading the active and the reactive powers. Okay, so here we also have the option to vary the reactive power that is given out by the inverter. And bottom is at the bottom you have this inverter panel. Okay, it is in a MPPT mode. These are different electrical parameters that are associated with that inverter. Maybe it's a DC bus voltage or its power factor at which it is operating currently. And this is the MPPT tracker live. And moving back to the root, currently you can see this message called as co-simulation disabled in yellow. Okay. In order to enable the co-simulation, here you can see the combo box which is saying enable open DSS. So we have to just click here and say true. Okay, as the result of which you can see now the open DSS side Scada panel has got activated. Okay, so the purpose of this open DSS panel is to give or display the instantaneous voltages, the three phase voltages, and uh, the phase angles at the respective phases. Okay, and it is generally doing the load flow analysis from the Typhoon Hill model. Okay, so generally this direct analysis is not possible, so that's a reason the open DSS model has been used here in order to do the load flow studies. Okay, next if we click on this generate power flow report button, you can see the power flow report is generated. Okay, which is giving you the name of the bus along with the phase 1, 2, 3, and the kW power and the kVAR power that it is injecting at the current state, and the kVA power and the power factor of the respective phase. Okay. Okay, so this report opens in the notepad. Okay, external to the software. Okay, we can vary the reactive power and accordingly see the change in the bus voltages. Okay, and we can again generate the power flow report. Okay, this is the co-simulation with OpenDSS. I request any participant if you have doubt, please go ahead and ask. Okay, in that case, there is no doubt. We will move on to the next model, which is IEEE 34 node test feeder. Okay, the IEEE 34 node test feeder is also found in the power systems, and here we have this IEEE 34 node test feeder with islanding detection with artificial neural network. Okay, so it's a vast model. As you can see, there's an application note that is associated with it. You can go through it. Okay, these are the different sections in which that entire system is divided. Okay, and this is the Scada panel. Okay, so now we'll open that model. Okay, this is the model you can see. Okay, there are nodes for measurement as we demonstrated it in the 4 node test feeder. Okay, this is the grid side. Okay, this is the contactor which is converted into the subsystem. For references, the same V reference, the way we collected in the IEEE 4 node is present over here. This is a model of the transmission line, and followed by there is this grid fault injection box. Okay, so it can enable you to add the fault. Okay, the including the fault resistance. As you can see, all these faults can be injected: the single line to ground fault, or the double line to ground fault, or the three phase fault, or the three phase to ground faults, or can be all can be injected using this. So this you will find these boxes present at different locations. Okay, okay, there are reactors that are connected. Okay, these are the loads at the intermediate distances. And next we have some sections of the transmission line, and here we have the voltage regulator model. Okay, so here we again have a single load. Here also we have a load. Okay, so next we see here there is a again a constant impedance load. Then there are small loads over here. There is a fault box. Okay, there are contactors in between which we can control from Scada. There are again loads. Again, there is a three phase load. Okay, then here there's a transformer and the load with the transmission line. This again has a three-phase load connected. uh, Here again there's a three-phase load. Okay, again there is a load, and on the other side of this we have our uh, distributed energy resource, which is a wind power plant that is connected. Okay, all this part we have already traversed. This part we have already traversed. Okay, so this is the wind power plant, the average model of the wind power plant. Okay, along with its UI that is connected over here, along with the measurement node and the interfacing transformer. Okay, so you can see the average model is again modeled as a controlled voltage source. Okay, and that is all about this model. And now we are going to open it in the Scada panel. Okay, there's a DG source here. Okay, there's a grid here, and at different locations on this grid there are loads and the fault injection box is present. Okay, so we are going to load this model in the Hill Scada. Okay, so we'll load it. Sorry. Okay, so we select our panel file. So this is the panel, and since it's an ANN based model, so we have to train this ANN for 5 counts. Okay, there's a counter here. Okay, down. Okay, if you see my arrow, so here is the counter, and I'm going to rerun this model on the first place. Okay, and this is the single line diagram. As you can see, this is the same replica of the existing circuit, and here is our wind power plant. Along with there is a capability of changing the wind speed. Okay, so in order to train this, uh, okay, here there are check boxes you can see. Okay, these check boxes are meant to open or close the circuit breakers which we saw initially. Okay, wherein this ANN based algorithm has to detect the islanding condition for this grid network. So currently you can see there is a training mode that you can select here for the artificial neural network, whether it is in training mode or the testing mode. So first we have to put it in the training mode. Okay, so you will see that the training LED will glow over here. Okay, and then we have to refer this training section. Okay, after that we have to we can try isolating the grid from the network. Okay, we have to open this contactor. So I'm unchecking this contactor. Okay, as you can see, the islanding LED is glowing over here. Okay, next I'll close the contactor back. Now I will disconnect the distributed generation. Okay, I'll reconnect it. So as you can see, the capture counter is advancing by 1 with each action which we are performing on this network. Okay, again we can open this grid, and now the capture counter has reached 5. But again, if I close this contactor, it is going to reset to 0. Okay, so that has completed the training process of this neural network. Next is to place it in the testing mode. So to move it into the testing mode, we are going to click and select testing. Okay, in testing, we are going to again repeat the similar procedure. We are going to open the grid side. You can see it is able to detect the islanding. Okay, with accuracy of 100%. Okay, if I close again, it is connected with the grid. It's in non-islanded mode. Okay, next I open the DG. You can see the islanding is detected with a 100% accuracy, and then we close this. Okay, so the islanding detection is off. So that's how the islanding detection works. Okay, you can try on with the harmonics and or the pure sine wave here by changing the grid parameters. Okay, you can also vary the wind speed here. Okay, the corresponding change in the output of the wind power plant is visible on this trace graph. Okay, along with that you can introduce certain short circuits in the network. Okay, and you can see the response of the output PV power. Okay, so that concludes the demonstration of this IEEE 34 node test feeder. Okay, if you have any doubt, please go ahead and ask. Otherwise, we can move on to the next model of the microgrid. Okay, so we are moving to the next model of the microgrid. So the next model is present in the microgrid section. So you have to go to this microgrid section, and here we have the microgrid example, and here you can see it's a plug and play microgrid library and testing for microgrid controller. Okay, so there's an application note associated with it. For more information you can refer it to that. It has the description of the controller part also and the SCADA. Okay, I open the model. Okay, so this is the microgrid model. Okay, starting from top, this is the microgrid controller. Okay, in case you're testing a new controller, you can use your own controller to test. Then this is the PCC monitor or point of common coupling monitor. So this is going to give the status of the power that is flowing between this grid and the DERs. Okay, between the loads that are connected to this distributed energy resources, and accordingly it is going to zero the power occur when during the switching. Okay, to minimize the transients. Okay. Okay, this is the microgrid controller. Okay, not going through the details. Okay, so here is the battery energy storage interface through a transformer. Okay, there's a transformers here in this subsystem. There's a wind power plant. There's a PV power plant. There's a diesel genset. Followed by there are loads connected to this network. Okay, the constant impedance load, the interruptible load, and there is a special load called as VBR, voltage behind reactor variable load. This can be controlled through the Scada panel along with this interruptible load. Okay, which we can connect and disconnect. Okay, with that we load this model in the Hill Scada. Okay, so we open this panel. This model is to be simulated on the real-time simulator, but currently, since I'm operating it on the desktop PC, it is going to run a bit slower. Okay, this is a single line diagram. As you can see, there's a PCC monitor. Okay, and these are the distributed energy resources that are connected. Okay, along with the load, and here you can change the variable load, or you can interrupt the load. Okay, so this side it is load control. Here you will see the different parameters that are linked with the distributed energy resources, including the battery inverter, the wind power plant, PV power plant, and the diesel genset. Okay, so zooming into the panel, from the top you can see this is the microgrid controller side. Okay, in the microgrid controller you can choose which DER is going to form the grid. Okay, so the grid forming DER it can be battery inverter or the diesel genset. Okay, so I can change it to the diesel genset. Okay, and the operating mode here you can select whether you want a grid tied operation or the islanded operation. So if I go to islanded, you can see the respective changes. We'll be able to see the changes in this phasor and the power that is transferred to the load. The model is running very slow. That is approximately 10 seconds or the 15 seconds slower than the real-time simulator. So that's the reason that the changes that are visible on the screen are updated after 10 seconds. That is 1 second of the real time is equivalent to the 10 seconds on this computer. Okay, I forgot to enable all the converters of this DER. So I'm enabling the battery inverter. I'm connecting the wind power plant. I'm connecting the PV plant, and I'm turning on the diesel genset, and then I'm enabling their converter. The visibility is bit less here. Okay, you can see the LEDs on this DRs that are coming on, but the diesel genset haven't been on yet. Okay, so it will take time to turn on. It is started, but it is not coupled to the grid. Okay, here we can change the variable load on the grid, and the interruptible load I'm going to switch on such that it will get connected and this LED will glow. As you can see, the load is connected now. Okay, here are the different waveforms pertaining to the different distributed energy resource. Here are the powers related to the load. Okay, next you can inject the fault in the grid. Okay, here we can set this to capture the fault. Okay, here the responses of different DERs can be seen. Okay, I'll select this portion. You can see the response of the battery ESS here, the wind power plant in the next viewport, and the PV plant in the next. And finally, you can see the response of the uh, diesel genset. Okay, after that, we close this. Okay, the individual load powers can be seen here in the sub panel. For example, starting with the battery inverter panel, followed by the wind power plant, okay, next the PV plant, and the diesel genset. Here the mode for the diesel genset can be chosen. Okay, so with that, we are done with the demonstration of the examples that were set for today. So if anybody has any doubt, please go ahead and ask. Hello, sir. I think there are no doubts from the participant side. Hello, Jenna, sir. Are you there?
Prajay, is your demonstration completed?
Yes, sir.
Can you
Uh,
can ask for participants regarding the queries?
so yeah, I did ask. Nobody is replying. I think they are not having any doubts.
Acha, hello.
Hello. Yes, sir.
Actually, whatever you are showing the example, that examples are very, very complex. Okay. Is there any simple examples are there? For
So
example,
sim- yes,
simple PV
yeah.
system,
So
grid connected, and
yes, there are.
if you show or that will be better. Okay, because that complex microgrid it is which is very difficult to understand
Yeah,
this
right.
stage. This. Okay.
No, sorry. This is also kind of complex only. This is DFIG based wind energy. Hmm. So you will like to see the simple models on which part you said you want a PV part or
Anything PV grid connected PV system or grid connected inverter control like that.
okay. So the grid connect.
Prajay,
Yes,
yeah,
yes.
grid connected converter you can go with.
Yeah. So this was already demonstrated last time.
That is
So any
not
yeah.
I
So
think that
so this was already demonstrated. The yes. So for PV it is easy, wherein you are just interfacing, replacing this DC. I mean DC source with the PV. Just a
no
second,
no.
sir. Yeah. Yes, sir. Please tell. I think this should work. The single phase PV inverter. So this is the comparatively simple uh, uh, grid connected single phase PV inverter, as you can see. Okay. So
If you
here is the PV
have any
connected.
PV system, MPP,
So your voice is breaking. I'm not able to hear. Simple what?
not and
So I'm not able to hear you properly. So this is comparatively simple, but still there are many subsystems here with integrated together. If you see, these are kind of nested subsystems which are there. Okay, so this is the current controller, but still there are nested subsystems inside. Okay, so this may look it up appear like a complex model, but if you ignore the subsystem, then otherwise it is comparatively simple than whatever we have demonstrated so far. So okay, these are the inputs and the outputs. Okay. So here we have to enable the inverter first. As you can see, the MPP point is not tracking currently, so it is here down. So first I'll connect. I will close the switch for the inverter. Okay. After that, I have to enable the inverter. Okay. Now you can see the MPPT point has started tracking the path. Okay, now the system is operating at the maximum power point. Okay, this is the simple model with independent active and the reactive power control. Okay, if you enable the Q mode, I will add the current here. Okay, so here that inverter can be set to export reactive power on the grid. So as you can see, there is a mode called Q mode. So if it is disabled, the inverter injects the power into the grid at the unity power factor. As you can see, the current and the voltage in the second port are exactly coinciding. Okay, and if I enable that Q mode, okay, you can see there is a relative phase shift that is produced between the output voltage and the current of that inverter. Okay, and this is how it gives you the control over the injected reactive power. And here you can see the power factor of that inverter. Okay, currently it is operating at 0.76 because it has to export reactive power to the grid. But if we remove the we disable the reactive power mode, then it starts operating at the unity power factor. Okay, you can see the system frequency, the DC link voltage, and at the output you can see the active power, reactive, and the apparent power, as well as the power factor measurements which are there. And here you can also change the irradiance and the temperature for the PV model. I think this is the conclusion of this model, but this is comparatively simpler to handle simple to handle compared to the complex microgrid, which I have demonstrated. So is it fine? Hello, sir. Are you there? Hello, sir. I'm done with the presentation. Are you there? Jenna, sir?
Okay.
So your voice is not audible. I think there is some glitch.
So can you send the files that example you have covered in last few days? So in addition to the examples we have
Yes.
already.
Which example exactly you want? The Yes, sir, sure, sure.
No, no.
The current
Whatever the example we have developed.
today and the
Okay.
last times, right? The other
Yeah,
day,
yeah, yeah.
both the days you want.
Both they both. Okay.
Okay, sir. Okay. Yes, I'll make sure I'll forward it. So
Okay.
although those
And one,
models are already available in the examples, but still I'm sending
no,
it.
no, one another thing is that okay, that my students, one of my students has
Yes,
sent
yes.
some papers to you. Okay. So can you help that
Okay,
that particular converter topology? Okay. If you
okay.
help us, I think that will be better. Okay.
So you have that student has mailed the paper, right? I mean the
In the very
details.
first, uh, two paper has sent to you. Okay.
Okay,
And
okay,
that paper is already actually published. Configuration of inverter is already published. Okay.
okay,
So if you can help us regarding that development, how, okay.
okay, sir. Sure,
So then it
sure, sir.
will be very good for us.
Okay, sir. Okay,
You check the mail that at the very first day he has sent to you. Okay.
Okay, sir. Got it.
Okay. And regarding the software installation else, okay. If we need some help, okay, we will definitely contact you. Okay.
Yes, sir. Sure, sir.
Also. So okay. Bye. Okay.
Yes, sir. Bye, sir. Thank you all the participants.